Welcome to this lesson on the ideal gas law. The question of the day, what characteristics make a gas ideal instead of real? Remember Avogadro, the guy who was given credit for the mole concept? Well, this is how he came up with it. He made the determination that if you had equal volumes of gas under the same conditions of temperature and pressure, they would have the same number of gas particles regardless of their identity. So it doesn't matter if you have hydrogen or helium or argon or xenon. If you have a equal volume of different gases at the same temperature and pressure, they will have the same number of particles. And this is where the concept of a mole was really born. Mathematically, Avogadro's law can be written like this. The volume of a gas divided by the number of moles in the before situation would be equal to the volume of that gas divided by the number of moles in the after situation. This 1 and 2 are not partaking in the equation per se. They're kind of like subscripts that describe the volume divided by the number of moles. We just as easily could have done this with a B and A for before and after, an A and B in place of 1 and 2, or an F and I for final and initial. This brings us to the concept of a molar volume. If you look at each of these balloons and you take a look at the periodic table, we have 1 mole of each of these gases, and we know this by looking at the mass. We have a molar mass of neon, hydrogen, chlorine, and carbon dioxide. When Avogadro was doing his experiments, he determined that the volume of these balloons would have been the same if the temperature and the pressure were the same for each balloon. And that led him to the concept of a molar volume. So again, it doesn't matter the identity of a gas, but if you have 1 mole of that gas, it will occupy 22.4 liters of space. Once more, this does not depend on the identity of the gas. If we take the combined gas law and rearrange it with the molar volume or Avogadro's law, then we come up with a constant. That constant is part of what we call the ideal gas law. If you know 3 of the variables in these equations, then you can figure out the 4th using that constant. Together, they create the ideal gas law. PV equals nRT. P stands for pressure, which in this equation has to be in atmospheres. So if you have a pressure that is not atmospheres, it must be converted. V stands for volume in liters. Again, if your volume is not in liters, it will have to be converted. N stands for the number of moles. R is that constant that makes the equation work, and it is the same everywhere. The relationship here boils down to this R constant, 0.08206 liters atmospheres per mole Kelvin. So those units in that constant will remind us that each of our units in the equation must be liters, atmospheres, mole, and Kelvin. So lastly, our temperature, capital T, is temperature measured in Kelvin. Again, if you get a Celsius temperature, you will have to convert it in order for this equation to work for you. If you know just 3 of these variables, you can figure out the 4th, and R is always going to be that constant. So you can solve for pressure, volume, number of moles, or temperature. The ideal gas law is a combination of those 4 prior gas laws, Avogadro's law, and then the 3 that make the combined gas law, Boyle's, Charles, and gay-Lussac's laws. In order to solve these problems, you would just use algebra skills, and this will come in handy when we talk about gas stoichiometry. So stay tuned for that. Subscribe so you don't miss it. Please leave any questions you have in the comment section below the video, and I'll see you in the next one. Bye.